All right, good morning, everyone. Let's get started with today's exercise. I'm really excited about this exercise for a couple of different reasons. One of them, today we're going to be talking about XGBoost, which is one of the highest performing machine learning algorithms across data hackathons. But that is the least reason that I'm excited about. The most important one is today we're going to have my PhD student and TA of this course, Amrinder Jakar, to be teaching you this content. So Amrinder has been doing a lot of machine learning on his research. He's very well versed with a lot of these techniques, and he's a TA of the semester. Maybe if you're not here in Athens, you may have not seen him, but he sits in every class since the beginning of the semester. And as part of his TAing, one of the requirements from my side is that he developed a lecture, a lab, and presented that to you all. So today he's going to be doing that. He developed some great material. I'm actually jealous of how much effort he put into it and made it really nice. A lot of graphics, a lot of really great information to help you understand XGBoost. You're going to look at his script and hope that he was teaching the whole semester, because my scripts don't look as nice as his. So I'm very excited for you to be learning today with him. I'm still going to be here in the room. I asked that, so I'm going to be watching Amrinder teach and provide him feedback on how he can improve, what things he can do better. From your side, whenever you get, we're going to have a time on this semester that you're going to be asked to provide student feedback. Most of your feedback is going to be related to my teaching, of course. But then if you have any thoughts about Amrinder's performance or something that you'd like to provide as feedback to him as well during your student evaluation, you're welcome to do that as well. All right, with that, I'm going to turn it over to Amrinder. Well, I guess before I do that, just a reminder, I did share the partial script for this exercise earlier this morning and asked you to create the full exercise on your side. So starting on GitHub, cloning, creating the folders, moving the partial script into code, and then copying and pasting the same data we've been using for the previous exercises into the data folder of this project, which is the 14_XGBoost. Assuming you have done all that, you should be good to go. Are you going to tell them about the source and visual? Yeah. Okay, perfect. All right, so I'm going to turn it over to Amrinder, and I'll be here in the room as well if anyone has any questions for me. But today the podium is for Amrinder.
Thank you, Dr. Bastos. So good morning, everyone. So for the just reminder to online students, please turn on the camera if you haven't. So as Dr. Bastos' class, in starting, we will talk about the learning objectives, like what are objectives for today's class. So I want to, because this is the last class for the machine learning, so I want to little bit revision for the previous machine learning algorithms or the content which we have Dr. Bastos told. So revision for you all. And we will understand about the XGBoost algorithm. I love this algorithm a lot, specifically in the machine learning, because it is very good in a couple of ways. So as for previous machine learning, for every machine learning, we have to do the pre-processed data, train our model, and then tune the hyperparameters, and then we will evaluate that how good that our model or algorithm is doing, or how we can improve it. So then I want to also give you a little bit explanation about the parallel processing. So as you, maybe few of you know that in our computers, we have more than one cores. So with more computational powers, like as sometimes Dr. Bester say that we take a lot of time to run an algorithm or we reduce some parameters. So if we have a parallel computational, it will do the faster process. So I want to show that how we can use this in R. And I want to today will tell you about one new concept that Latin hyperparameter tuning. And the other important function is that tune race ANOVA, that this is the function on the basis of different ANOVA. It will check the best hyperparameters and give what could be the best hyperparameter value, which we should use to get our best model prediction. So if you all have opened today's script, maybe for some of you, it's already in the visual, and which is on the top below the save button. And there is a two buttons, source and visual. If it haven't opened in visual, please click on the visual. Yeah, so I can show you. So if you can see the mouse, so where is my mouse cursor now? You see this, there is a source code and then there is a visual. So these are the two ways which you can show. So visual is like that. So this is like what you see is what you get. So however you see it's, you can consider it as like Word file. That's the same. So here you can do all the things like as you do the Word. So it's pretty good for the beginners if you have to write a paper, like as you, Dr. Best was saying. This will show you in the same way how you see when you render your file. So the other thing is, like as you see on the top, that there is if you want to bold anything, italics, notepad, there are some of the functions which you use in the Word. So for writing a paper or writing any report, this could be very useful. And this the other good thing is that on just one click, you can switch back to the source. But once you get comfortable, like know a lot about R or the Koto files, I still recommend to do everything in the source, but just for the visual purpose, like how your file will look after you render, or if you have to add any extra text, visual is very good. It gives you very good graphs, pictures. Like sometimes on source you have to click to bring the picture, but on visual it's automatically bring. So if you want to show something on the go, it's very good.
Yeah, so I was just curious, when you end up rendering the part, does it mess anything up? Or is it just like, if you're on the visual page, it'll look exactly like this?
It will exactly look like this once you render the file. So if everything is if there is error, you can't render it, but in visual, you can still see that. But if there is any error in your code in the source, so it will not render. But if everything is good, it will exactly look the same as it is looking in the visual. Any other question or any online question for this? Okay, so next move to our like little bit background, which we are teaching in previous classes which Dr. Bastos have told about the machine learning. So the first model, if you remember, which Dr. Bastos is told you the ridge regression, or which have the L2 penalty. So if anyone remember about that, or that when we have to use L2 penalty, what are the pros, what are the cons of that? Anyone from the online, if you guys remember? So if no one remembers, don't worry, we will. So we use it handles multi-collinearity by shrinking the coefficient. So the good thing about this, it doesn't remove the coefficients. So if you remember this picture, so it brings all your coefficients, shrinks the coefficients near to the zero. So rather than removing coefficients, it shrinks. So that's how it handles the errors. And moving to the next, which is the lasso regressions, that is L1 penalty. So the major difference is between this, that it shrinks, but in lasso regression, it removes the non-important variables. So the variables which it thinks it's not important, it removes. But if you think that you should, all the variables are important from your knowledge that you have to retain them, so then it's not recommended to use the lasso regression. So the next regression which Dr. Bastos told is the elastic net. So it brings the like both together. So using both, so first you can shrink your coefficients, and then it will bring closer to the zero. And then if you run the lasso coefficient, it removes the unimportant coefficients. So you can have the power of the both. So because if you directly use the lasso, maybe it removes some important coefficients which you want to still retain. So using that, it may help you to have the power of the both. Moving to the next, which is the tree-based method. So the first model which Dr. Bastol is the conditional inference trees. It's pretty good algorithm, specifically when you have to see that how the things are impacting to how the model is working. So it's pretty good model to show based on the tree and based on the statistics that which variables are important and how the algorithm is working. So moving to the next, it is the random forest. So it is still as same as the tree-based model, but as it say the forest. So when you have the multiple trees together, and when you take the average of that, that's the random forest. But it has its pros and cons as you have discussed in the last class. So if you have any questions about the previous models, you're welcome to ask, because now we will start about XGBoost. No questions?
What is an algorithm? Because I tried to understand the word, like how would you explain something like an algorithm?
So how to
Is it like a model?
a model or equation, like whatever could be. So like we have a question here that what could we say an algorithm? So there could be like different algorithm types. Like what I understand that whenever you have an equation, statistical approval that how the things are working behind that, there could be some algorithms are very small, very simple, like regression, or but there are some like complex, like random forest, XGBoost. But whenever you have the equations and stats in that, I think that's the algorithm. May Dr. Bastos want to add something to this?
So, I mean, because we have critical steps, this related steps behind it. But even like if you develop like a program where you're just doing, let's say, you give a data set and doing rendering, mediating a function, that can also be considered an algorithm because you have steps of sequence of steps of how you're doing it. But here specifically we're referring to statistical algorithms, which are basically different algorithms are using different steps to conduct a certain analysis. As Ramindra was saying, so linear regression is basically one step, right? There's not a lot more to it. But when you think of like random forest, which we saw, we have many steps where we first develop a single tree, and then develop many trees, and then you have a forest, and now the whole forest is voting on the condition. So it's like a sequence of steps.
Okay, so let's start. Oops, where it's. Oops, okay. We can't hear online. Oh, maybe you haven't turned on. Maybe I turn on my, if you want to repeat.
Can you hear me online now?
Yeah, we can hear you.
Do you want to?
You want to repeat?
Yeah. Yeah, that works. All right. So I was just saying here, so the question from Charles is, what is an algorithm? I was just saying that an algorithm in general terms is just a sequence of steps that happen in sequential order. In our case, specifically, we're talking about statistical algorithms. So it's just going to be what steps that specific analysis is conducting behind the scenes to work, right? So Amindra was saying earlier, giving the example of linear regression being a very simple algorithm. But then if you think of, random forest, which is what we saw before, there's many steps to that, right? So we first do a random sampling, a bootstrap sample of the rows, we give to each tree, and then each tree at each split is going to select just a portion or randomly selects only a portion of the columns, and then building the tree based on the node size. And then it builds many trees as in a forest, and then the whole forest votes. So each one of those steps would be a step in the algorithm, right? So in general terms, an algorithm is just a sequence of steps that we follow for a given task. And in this case here, a statistical algorithm is just implementing those steps using a statistical framework. All right, so.
Okay, so next move to the introduction about the XG. Okay, let's move to the introduction about the XGBoost. So as the name suggests, so the full name of the XGBoost is the extreme gradient boosting. So as we have seen the gradient earlier in the random forest, and this is like a very powerful and scalable machine learning algorithm, which is based on the gradient boosting. So it is very powerful for both tabular data and structured data, but it can be used for the classification, regression for the both of that thing. So unlike like the random forest where you have the trees are independent. So like if you remember that in random forest, each tree give its decision or predictions. And then at the end, we take the average of that. That's how the random forest works. But in this, each tree gives its prediction with the errors, and then the next tree learns from the errors. I will explain in next couple of minutes that how it works. But overall, that it's learn in the sequential learning from one tree to the next and having that all the parameters like what are the laws. So it learns from the previous tree and try to learn from the mistakes and improve in the next tree. So XGBoost also like supports like parallel tree constructions, regularizations as it helps to not to overfit the data. It can also work with the NA values, same as random forest. It has a custom loss function and it is like much more efficient with the memory usage and computational power, because here we can run with the parallel. We can use also in the random forest parallel programming, but it's a little bit complex. If anyone later on after this class want to learn in random forest too, have the code for that, I can share that too. So what are the like key differences between different tree models? Like as the decision tree, it have the only one tree and it will tell the model its predictions that whatever prediction it gets. Next, moving to the random forest, like as I said, it's different. It is a forest. There are different predictions of the models from the different trees. And at the end, it takes the average of all and then give the prediction. So coming to the XGBoost, I move a little bit down, like it's a little bit better. So tell you the process of the boosting. So like here you can see that you have the training set in the all your whole training data. Then there is a subset of training data is taken and it was run a model. Maybe that could be a weak learner model. And then maybe there will be some false predictions from that model. But then there will be the second tree from the same, and it takes the fall predictions and whatever the predictions, and then it will have the maybe second prediction. So like this, there could be like a lot of trees, like as in forest. So when there will be like a lot of weak people combined, it gives you a better prediction model compared to the random forest. So the overall major difference between these two is the between the random forest and the XGBoost is that in the random forest, trees are independent of the predictions. But in XGBoost, one tree errors is passed to the next, prediction is passed to next trees, and it learns from the previous tree. And at the end, when all the tree combines its predictions, it gives a pretty good prediction compared to the all the machine learning models. So weak learner, like if there could be like a one model in the starting, maybe the first model can't give you a very good predictions.
Maybe like a tree that's very shallow, perhaps.
Yes, like yeah. Yes, like in the starting, we show you the one tree, it could be like that. We don't give you much, but when you have more trees and they're learning from each other, that it gives you better prediction at the end. So everyone got it right, because this is the important thing. This is the major difference, that how then any XGBoost works. Okay.
So the subset setting is based on the specific information, just for the training set, like how do the subset in our data?
So like as we do the subset in, so okay, sorry. So for the online person, so Charles is asking that how the subset 2 data is set. So like as for the random forest, there are different hyperparameters. You can also choose that how you want to get your subset of data of the, but I will talk about that hyperparameters in the incoming, but it's almost the same as random forest. Okay, so moving to the next, that this is the assemble learning. So I think I have told you already that what's the sample learning, but just to make things more clear, it's the sample thing is combines like multiple models. Sample learning is working in the both in the random forest and XGBoost when you combine multiple models together and get the prediction together. So that is the assemble learning. You can see in this picture. This is picture from from the random forest where there are a lot of trees, and then at the end they give one common prediction. So there are two types of assemble learning. Like as I mentioned, like there could be for different for random forest and for XGBoost. The sample learning which we are using for the random forest, that is known as the bagging, and which we use for XGBoost is known as the boosting. So from the name, you can understand that what is from where the bagging and boosting works. So coming to the figure below, because I think figures are more easier to explain rather than the words. So the first is the bagging, which we use in the random forest. So here you have the original data set, and then you have the different models like model 1, model 2, up to the model N. And then consider that some models say that the plant is infected, and maybe few models say that plant is not infected. And then it takes the average. So if the more model predicted that the plant is infected, our overall prediction will be that plant is infected. But like in boosting, as I mentioned, that we will run the model 1, then model 2 will be based on the model 1 predictions, and then it will go to the next to next. And then we will get the final prediction. So it learns from the all, and then it gives you that whether the prediction is plant is infected or whether the plant is not infected. So this is the concept of between bagging and boosting. So as you see that we ran the one model, it's you giving little bit less accuracy. As you ran the second, you go more and more. So like when you have 1024, this is just an example. See, our model is fitting pretty good with the raw data. So your prediction will be also very accurate compared to if you just run one-time model or if you take the average of them. So yes, yeah.
So, yeah, so for when we do like as in boosting, you said that it learns from the last mistakes, like.
Yes.
Okay, but how it will impact the false prediction? So it will have more false prediction?
So it will have less false prediction because it knows that what are the false prediction in the model first. So it will not take that false prediction in the model 2. So if there are like 4 models, they don't know that what are the false prediction in each. And later on, you take the average of all the false predictions. So you will have more false prediction. So coming to this picture. So next model. So like if you have seen the training data set, so you ran the model 1. So it have known that what are the incorrect predictions in the model 1. It will not take that, whatever the correct predictions will be there, it will not take into the second. So it knows that what are the correct predictions, and the model have to figure out what are the incorrect predictions and how to make them more correct. I'm right, Dr. Bastas? Okay. So coming to next, that is gradient descent boosting. So like as from the boosting can work on many loss functions like RMC, log, loss, there could be like different. So coming to like gradient boss, so it measures the loss error between the prediction and the actual. So what are the common loss functions which we have learned? That could be like RMSE, log loss. And as Dr. Bastos asked that what is the weak learner? So here I have written that if anyone want to read it later on, that if we have the shallow decision tree and it is trained to predict the residual layers in the previous model, it performs like slightly better than random guessing. So as you get more and more trees from the previous, it's increase its prediction more and more. But like there are the pros and cons. If you have a lot of trees, it's more computational power. Sometimes maybe you overfitting the model. So for that, you have to work with the hyperparameters, that how to properly play with the hyperparameters. It should be properly tuned.
Hey, Amrinder, I got a question. Like
Yeah.
for this learning rate, when you tune the hyperparameter, like do you have to check with the increasing learning rate and decreasing learning rate, and how does this how does that model, typical model, can predict? Is that right?
So yeah, that's right. And we will see while we were working on the code that how we can see that it should be like how fast should be your learning. Because as you can see that if your learning is very less, then it will get the too big, like you can see in the right. And if your learning is too small, you will get a better predictions, but problem is that it will take a lot of computational power, and sometimes you don't have much, our computers don't have that much computational power. So you have to be found a proper balance that what could be the right.
Gotcha.
So I just want to expand a little bit on the 3 steps to gradient boosting that Aminder just talked about. Can you go up to that part of the code, please, Aminder?
Okay.
So here, I think is the first time that we may be talking about a loss function. But just to remind you, so a loss function is what the algorithm is trying to optimize. So in our example that we've been using a continuous variable, then our loss function can either to minimize root mean squared error, or maybe to increase or optimize R squared. So that is our loss function, is what we're trying to optimize through here. Because today, some of the examples that Aminder is showing you on the figures has like a classification example. So you see like correct classification or wrong classification. That would be, you would see that type of setup if your predicted variable is categorical, right? Which is not our case. So in our case, we do not have incorrect classifications. We just have residuals, which is the difference between what the model is predicting and what the actual observed value is. But just to connect a little bit with what Aminder was showing on his figures, as far as a correct or incorrect classification of the ones up above. Yeah, so here imagine that your predicted variable was categorical. So perhaps as Aminder showed in the previous figure relating to like disease detection, where your predicted variable is like infected or non-infected. So it's a category, right? There are 2 categories. So in that case, just to kind of explain to you a little bit and make the connection, if you're running a model, any machine learning model, if that model accepts categorical predicted variables, like in this case here, imagine your Y column would be a column that says infected or non-infected, then we do not use R square or MSE. Right? We use other metrics like accuracy or the false positive ratio or the false negative ratio. I mean, there are many others that we saw some of them in the slide set when we first talked about machine learning. So there are many fit metrics that we would use for the categorical predicted variable. And in that case, if you have a categorical predicted variable, your loss function then is also different. It's not going to be RMSE or R square, is going to be perhaps the overall accuracy. How many actual infected plants were classified as infected, or how many non-infected were classified as non-infected, depending on what is your interest in that exercise. But just to connect here, that your loss function first depends on your predicted variable. If it is a numerical predicted variable like ours, you would use things like R square or MSE, mean, absolute error, and others. And if your predicted variable is categorical, which we're not doing in at least not in our exercises, then your loss functions are different. They're the ones that you would apply for a categorical variable like % accuracy of that classification. So I just wanted to make the connection here with the loss function so people understand better. Thanks, Aminder. Okay, I'm going to mute myself. You can.
Okay, so like in this figure, like as you asked that what is happening in this figure. So by loss function is that our goal is to minimize the loss. So the below we come to the theta, like closer to that, the better the model is. So if your learning is too big, it could be overshoot that what could be the best parameters or what could be the best R square. So in that, but if, as I mentioned, that if it is too small, it will take a lot of time to learn, and it will take a lot of computational power to learn that how things are going on. So coming to like what could be like hyperparameters, there could be like a lot of the hyperparameters which you can like tune for the xgboost or for any other. So here I will just mention which are some important. So the first is which we also have learned in the random forest, that is mtry. So that is controls that how many prediction features which should be randomly selected to consider at each split when building a decision tree. So if you have like 100 features, so like if you have 10 features, usually it's recommended to get 30% at one time to show you the model. And for next time, it's show 30%. But you can also change this. So this is like one of the important hyperparameters which you should can do the tuning specifically if you want to tune xgboost and the random forest. So the range which we can in the XGBoost, it is also referred as the core sample by tree. So the range for this is range from 0 to 1. So you can consider that 0 as 0%, 1 as the 100%. So if you are choosing like 0.3, that means you are choosing like 30% of the total variables. And if it's 0.6, you're choosing like 60% of the total variables to be applied for that to show app at once. So next, why it matters, like if you show your all the parameters at once, maybe there could be the risk of the overfitting. Maybe you will overfit your model. So if you have show less like 0.3, it prevents to overfitting of your model. Any questions about this? That I think we have used the mtry in random forest too. So this is the same which we have used. So next come to the loss reduction, which is also called as gamma. So this is known as a minimum gain required to make a split. So it controls that what could be the minimum loss of improvement is required to allow the split between each tree. So like, as you know that there is the split between the trees. So without overfitting the model, so this should be known that what should be the minimum loss we need for the improvement.
So just make a quick comment here. Okay. So imagine that, so loss reduction here is basically just to say in a different way here. So imagine that so we have multiple trees and each one is learning from the mistakes of the previous one. Imagine that the first tree all of them are going to be weak learners, meaning that they're not going to be very deep trees with many vertical layers. But if you were to allow a given tree, I think we talked about this in random forest or even in conditional inference tree, where imagine that you could have as many terminal nodes as you have observations, where each terminal node is a single observation, a very deep, complex tree. That is not what we're trying to do, right? In that case, if you had that, you basically have your R-square as perfect because you're predicting every single observation because each one of them is in a different terminal node. That is not our goal. We want to find the patterns, but not to model the noise. So loss reduction here is just saying how much improvement in my loss function. So in our case, our loss function could be our MSE or R square. So how much am I reducing our MSE by making this next split? If that reduction is less than this hyperparameter, then that split does not happen. Just to kind of say this in a different way to help you understand. Thanks, Ramendra.
Okay, so next moving to the minimum observations at the terminal node. So as you can understand from the title, that how much number of observations at the end you need at the terminal nodes. So like if you have two less observations at the terminal node, the minimum which you can go up to is the 1. But if you have that less observations, sometimes model is overfitting and it learn lot. There will be a lot of noise in your data. So you have to decide that what could be like number of observations at your last terminal node. So like if you didn't decide that what could be the number of terminal nodes, maybe there would be overfitting of the model and model will have a lot of noise and so after there should be a certain thresholds that after each if you are getting X amount of observations and after it is not impacting your p-square or the like p-value or the ANOVA. So while tuning the hyperparameters, we usually use the ANOVA values, that what could be the number of observations at each terminal node. You want to add to anything to Dr. Bastis? Okay, so next moving to the tree depth. So for this, we have good figure, which I like. I think we have seen this in the, in the random forest too, that how tree depth can be impacted. So by tree depth is that, and so you have the first observational tree, and then how much more deeper trees you need, the more the trees you have, sometimes it gets more like hard to understand the model, but sometimes it's needed. But for both, if you have too much, you can't understand the model. So but sometimes you needed to do that. So like for the figure in this, so for the first figure, which you can see that you have only one depth. So in one depth, your model is like you have the S curve in the raw structure. So it is showing that house, but if you have only one depth, it's not properly, your model is not getting proper predictions. But as you increase the depths in your trees, so as you see, that is the last tree which is at the end, the model is properly fitting that. So that's how the tree depth is impacting that how could be model fitted there. Any online question about this?
Hi, Amrinder. Can you please explain what does that tree height means?
Good.
Can you explain the term?
So tree height, I don't know about tree height. Like I showed this picture is from online. So mostly what I heard about is the tree depth only. Maybe Dr. Bastos can know about the tree height.
Yeah, I normally don't see height. We normally see depth, which is the number of horizontal layers. I'm not sure where you got this image from. Maybe they have their explanation of what they mean by height, but it seems like perhaps they're defining height as the distance between the last layer and the terminal nodes. I'm not sure. Normally, we would think of depth. So this tree here, in at least what I understand, would have basically three, like a depth of three, right? We have three horizontal layers here.
Thank you.
It seems like depth is going down and height is going up, like height 0, 1, 2, 3.
Yeah. So coming to the number of trees, so as it saying that how many trees you should have in like your forest. So if you have here, you seeing that your error is, so if you have 0 trees or maybe like 10 trees, your RMS is for 30,000. So but as you increase the number of trees, so that means that how many trees in the forest, like one tree is running from the next. So as you increase the number of trees, so you can have more trees learning from the previous tree, so your model will be improved. But that is up to like some extent. Like you can see that after reaching about 250, it is almost constant, so the model is not giving you better prediction after that. So you can decide that how much number of trees you want to give at the time of the tuning this hyperparameter. So next is the learning rate. So as we have seen that in the earlier, that if you have like slower learning rate, then it takes more computational power. But if you have the faster learning rate, the model could be very, very fast, but maybe miss the better predictions. So based on the loss function and like model parameters, you can decide that how much should be the learning rate of your model. If you want to have a better model, it's suggested that you should go with the slower learning. So model can learn properly with time, but it takes more time and more computational power. So here, as in this figure, I'm showing that if you have the lower, so on the top, there will be the learning rates. Sorry, it's of the black color, that's why you can't see. But just to tell you that there will be like in the first 0.001 learning rate, and on the last it's 0.5. So as you can see that learning rate is increasing, the model prediction is increasing. So in the starting, you have only like 0.78. So like there are different colored points, that's red and green, red and blue. So how the model is assigning in different parameters. And in last, you can see that as the learning rate is decreased, and in that is 0.95 accuracy. So that is like, as you reduce your learning rate, your predictions of model can be improved, but it takes more time for the model. You have any question?
So can you explain, so I understand that each column here, so we have the initial data on the left.
Yes, this.
And then we have one grades. Columns.
Yes.
Rows.
So different rows. So on the top, they have shown the learning rate, but for the next rows, they haven't shown the learning rate, but they are the different learning rates too. So after like 0.05, they have in the, from where I picture have took, they have gone more further. So they have decreased more learning rate. Okay, next coming to the sample size that, so it controls that how much, so as in random forest also we see the sample size, that how much rows of the data you should show the model that randomly how many rows it should collect. Like if you have 1,000 of rows, then you can tell the model that how much each time, how many rows of your data is provided to the model. Like initially, like Charles have asked that what could be the training set. So from this, you can choose that what could be your training set of data and what could be the number of rows. So as same, if you have the, it's ranging from 0 to 1. If it's 1, then you have all the rows giving to your model. But if you're giving like 0.5, your 50% of the rows will be shown to the model. So coming that we have discussed about that XGBoost and the random forest. So like what are the both algorithms are pretty good, and what could be the like basic difference? The basic difference between both of the models is that random forest works on the bagging, and XGBoost works on boosting. So that's the uh, uh, basic difference. And next move to like what we have the pros and cons of the XGBoost. So like as XGBoost can provide you the high accuracy, it builds both on L1 and L2 regularization. So it helps not to overfit the data. So as it can have a parallel computational, which we will see once we were running the model. So it is pretty fast and pretty scalable. It can also handle the missing values. So it supports both regression and classification. So for like our data, we are using a regression, but for some, if you want to classify, like we're showing data points, you can use for that too. And it have like allows custom laws and objective functions, and it will help in offer pruning and early stopping. So we will hyper tune this parameter to that. I will explain that what I mean by pruning and early stopping with different hyperparameters. So as of the cons, this model is more complex as compared to the simpler models. Sometimes if you don't like tune hyperparameters properly, there could be easily overfitting. So as of same as a random forest, so if you have to interpret that how you are coming to that particular results, like for XGBoost and random forest, it's pretty hard. You can get the final prediction, but it's hard to understand that how you come to that particular prediction. So it requires scalability, and like for time series data, we are not using that time series data here, but if anyone from the class have a time series data, there is a other way. If you can email me and I can have that code to that, how to do that. So the other, that it is a supervised learning. So it's just work on the supervised, it can't work on unsupervised. So I see that there are some confused faces that we have the ELC quiz. So please go on. So if anyone have question? Yes, Charles. Parallel computing, yes.
Is it like something, I'm trying to capture like the whole idea. Is the speeding gonna happen in different?
So it will use different cores of your computer. Like currently they are using like sequential cores. So in parallel, your all the cores we can use differently.
So,
Yes.
so how would they communicate? Next node.
How do they communicate?
So,
So Charles was asking about how the parallel computing works as far as different, because in boosting, one tree depends on the previous tree,
Yes.
right? So how does that work? So what's gonna happen here is, so we're gonna do the parallel not on a given XGBoost run, it's actually gonna be a cross run. So when we do the V-fold cross validation, each fold is gonna go to a different core and be run independently because they are independent, right? But you can, yeah, you're right. You cannot separate it within a given run. You cannot separate it, especially on XGBoost, because each next tree depends on the previous one.
Yeah.
Right. So that's how we're parallelizing.
Thank you.
So, Aminder, just before we move to the quiz, I just want to stress a point that is here of one of the cons of XGBoost. So we noticed that we learned that random forest, one of the good sides of random forest is that it provides very good predictability, even if you don't fine tune it. We're still fine tune it to make it better, but it ships right out of the box in a pretty good format already. And it's tolerant, or it has its checks and balances against overfitting, right? So we talked about in random forest, you can increase the number of trees basically to decrease your error. But if you go past that number, you're not going to overfit. You're just going to use more computational power in random forest, but you're not overfitting because each tree is developed independently with a subset of rows and a subset of columns that it splits. XGBoost is not like that. It's really easy to overfit with XGBoost because each extra tree you're adding is modeling the noise of the previous tree. So if you add 100 trees, you basically have each one of them modeling the mistakes of the previous one. If you add 1,000, now we have 1,000 corrections of your mistakes. So there's going to be a point that adding more trees in XGBoost will definitely overfit, which is not the case for random forest. So again, random forest is very robust right off the box without fine tuning. XGBoost is very powerful, but it can very easily overfit. So we really have to pay attention to training XGBoost and make sure that we avoid overfitting. I just wanted to make that parenthesis.
Okay, Dr. Bastos, I just had one question.
Okay,
As
so let's go to ELC. Yes. Good. So we have a 5-minute timer for this. So it's just 5 multiple choice. So it will be sufficient. Yeah. So we can have a 5 minute of break. Let me. Ashwin. No? So Ashwin, you can go ahead if you have any question.
I am in there. Can you hear me? Hello? Can you hear me?
Oh, sorry. Ashwin, can you repeat?
Can you hear me?
Yeah, I can hear you.
Okay. Now, like, I just want to understand the use of orderly stopping. Like, don't we use this orderly stopping rule to avoid this, especially the overfitting
So we,
and the reduce the computational power?
so we will use early stopping.
So, I mean, like, if we are using the orderly stopping rule in for the XGBoost, I mean, like, is it still there is a chance to overfit the model?
Like if you do, then may not it be like overfit, and it also depends like what type of data you have. But that's the thing that it is a pro. It is not a con of the XGBoost. Like if you use the early stopping, so then it can be very good.
Yeah, that's why I had a concern. Like, the major cons of the XGBoost is like there is a high risk of overfitting, right?
Yeah,
So
but if it's not carefully tuned, like for random percent, Dr. Bester mentioned that if you don't like do the hyper tuning, then also it gives you pretty good prediction. But that's not the case with XGBoost. So you have to do the hyper tuning. So if you don't do, then it will.
okay, I have the following question for this one. Uh, if we use the early stopping rule, is there any chance to make like the model underfitting or something like that?
I don't think so. There will be underfitting if you do the over like early stopping.
Okay, thank you.
Ashwin, can you hear me?
Yes, Dr. Bastos.
Can you hear Dr. Bastos?
Yes, I can hear you.
Okay, let me turn up my volume. So the thing is that our goal here is, so the early stopping is gonna help, especially determine the number of trees. And I mean, we're always trying to compensate that balance between bias and variance. And so the way that we're gonna be doing that is fine tuning, right? So early stopping is just saying that if you can train with 10, with 100, with 1,000 trees, but where should you stop in that case of number of trees specifically? So it's just helping us to understand what is the balance, right? And we're looking for that balance of not just number of trees, but all the hyperparameters that you can fine tune to what is it that helps us understand or model the signal and not model the noise.
Okay.
Yeah, does that make sense?
Yeah, I got it. Thank you so much.
Thank you.
Dr. Bastos, I had this like another quick question, if I'm not bothering you.
No, go ahead.
Like, uh, my question is about the learning rate and the tree depth. And like, what kind of combination generally we prefer for the learning rate, the combination when you tune the hyperparameter? Like, do we prefer the higher learning rate with the higher trade depth, or like the higher learning rate with the lower trade depth? Or like, is there any like some good combinations of these two hyperparameter?
It's a trade-off. You wanna, I'm in there. It's a trade-off, right? So, I mean, a lot of these hyperparameters, there's going to be a trade-off between them. And the thing is that it's going to be, I mean, although I'm not, there's probably some default values if you just run the model without fine-tuning. But the thing is that all of these machine learning models, we're always going to be using your data that you're working at that with that analysis to help you determine that. That's basically one of the concepts within machine learning, right? Is that you're learning from the data itself. So these values will change depending on the data set. Perhaps some data sets, you having a larger learning rate would be better. Others having a lower learning rate would be better. It's really going to depend on how much variability you have in your data, how good are your predictor variables, how much noise you have in the data as well. So it's really, again, the key here is that we use the data we're working with to teach the algorithm how complex it should be before it starts modeling noise. And that combination of complexity is going to come from all your hyperparameter values, which again, we have to train them, right? We never know what it should be before we get started. Does that help?
Yeah, thank you.
Awesome. Thanks, Ashwin. All right, I'm going to mute here, Minna, you can.
Okay, guys. Oh. Now let's start. Oh. Now we're going okay. So as always, we have to install some new packages. Like I don't think so. If you have the xgboost, please uncomment it. And oh yes, so please go to the source. That will be easier. I know that you can run code in Visual too, but it's better to use source when you're running the code. So I think I have given the two xgboost, but maybe you don't have the do parallel too. So if you don't have the do parallel package, please install that too. So is everyone able to got all the libraries? Okay, so in this exercise, again, we are using the same data set, which we are using from last 3 machine learning classes, that is weather data. So just please load the same data set. And as for all machine learnings, we will begin dividing the data in training data set and the testing data set. Usually we are doing the same split, that is 70-30 split, and that is pretty standard split which we use. So if you go, we will split that in 70% as training and 30 as then. And as we remember that we use the strata to have the same data set for the training and split. So for the same distribution. So this is just run that pure weather train. Just you have see that you have 487 columns in that. And in test, you have 211. Is it same for all? Okay, so this is just to see the weather distribution, like distribution of your data set, that whether your train and test are same, because we have used the strata. So that's the reason we are getting the same distribution for the both data sets. So as for same, we have to normalize the data, like there should be some weather recipe. Normalize data, removing unimportant variables, dropping the NAs, perform BCA. So this is the same from all the previous exercise. So as we always see that what things we have to do with our data set, whether we have to normalize our data set or whether we need a new dummy variables. Like this is the same link Dr. Bastos showed in the previous class. So as you go, so for the if you have seen that for the boost tree, it is showing that you have to do impute and you have to do the dummy variables. So it's saying the x upon power the square. So it's saying that it's recommended but not needed. For the regression, you don't need to create dummy variables. But if you are using the classification model, like if you have to classify disease infected plant, not infected, then you have to create dummy variables. So here again, we have removed the GenFab, this data set. This is the same script which we're using in random forest. So coming to weather prep, again, same as from our previous, so will not explain much. So here the things where we will work like, and here the things which will get different. So here we will see that how to, there are different specifications of each algorithm. And here we will specify for the xgboost. So as for the, we are using xgboost package library for this. So the name for this is the boost tree. And here we will do the 4 hyperparameters. That is the tree, which is the tell the number of boosting rounds. So here we will work with 4 different hyperparameters. First is the number of trees, that is number of boosting round, that how many number of trees we have. Second is the tree depth. It will control that how each individual tree can how go deep. And the third is the minimum number. So it will be the number of observation required in each node for to be split. And the last, which Ashwin has asking, is about the learning rate. So as you see that, so if first hyperparameter which we are tuning is the trees. So just try trees. It is automatically coming from the XGBoost. And here we are tuning it. So here you can put the numbers if you have like a pretty good knowledge about the hyperparameter, like what could be the range, what could be the best fit. You can put a random like number from your knowledge too. But like if you're like me, which I don't have a lot of stats knowledge, like for each hyperparameters, then we will use a tune function. So we will tune it and it will bring the best hyperparameter, like what is the best number for number of trees. So later on, we will tune it and it will automatically get the best number for the trees for here. So similarly, we will do for the tree depth. So same for minimum n. And last, the hyperparameter which you're tuning is the learning rate. That is known as learn underscore rate. So as you have like in previous, for random forest, you have to specify like what type of the engine you are using. So here also you have to specify the engine. So this engine here will be the XGBoost, but it also depends like what type of library you're using. So here we are using the XGBoost, but you can use the different, there are different libraries for different machine learnings. So you have to see like what type of library you're using. But if, for this, we are using XGBoost, so just set underscore your engine.
Arminder,
Yes.
you need to put another parenthesis, the first bracket after tune. Learn underscore rate equal tune. You need to put another parenthesis before the pipe.
Oh, sorry. Thank you.
Mhm.
So third engine is XGBoost, and we have to set mode because it can do for both regression and for the classification. So you have to explain that whether you're doing the classification or whether you are using the regression. So in our case, we're using the regression. So if everything is good, if you run this, it should run pretty fast. Hope it ran for everyone. So online, if have any problem, please let me know.
Can you show me the code chunk?
Yeah.
Oh, thank you.
Okay. So next will be the like cross validation. So like last time we have ran it.
Arvinder,
Yes,
excuse me, can you show me the chart?
sure.
Oh, thank you. Thank you.
Okay, so next will be the like cross validation. So here last time we have ran like 5 cross validation. So here we will be, because we are using the parallel computer. So I think 10 will be, because usually 10 is recommended. So we can run 10. So code is already there. So just click on run and you will have 10 different folds. So next move to the hyperparameter grid with Latin hypercube. So this is something new, which we're gonna talk. So this will work. It is like a smarter. So it is a random sampling technique for like generating values for like tuning our hyperparameters. So like there are like different. We have used the grid search earlier, but that is like for XGBoost, it will be lot time consuming because it is very, very slow. It is more computational expensive than this one. And in XGBoost, we have used the simulated annealing. We can use the same for this, but again, it is this is a little bit faster compared to the previous, which we have done in the XGBoost. So as it's mentioned that if you write a grid Latin hypercube, it will automatically show. And then you have to just tell that what type of hyperparameters which we have decided on the top. That is tree depth and minimum number of nodes. Learn rate. And trees. So these are the which are hyperparameters we have decided on the top. Here, then you have to tell that how much number of combinations you need. So like for each of the for how many number of hyperparameters you will give them, then it will make the combination of the each. And then you can decide that how much combinations you have to tell. So for now, you can make like different 100 of different combination, and then we can choose which could be the best combination out of that. So now from each, like there are 4, so it will take like tree depth, and then it will take one for the minimum number learn rate and make one combination, and then it will take the tree depth to make the combination for second combination with the all 3 very hyperparameters. And similarly, it will make the 100 different combinations with each, and then out of that 100 we will choose what could be the best one. Anyone have question about this?
Amrinder.
Yes.
I'm just trying to put 2 and 2 together. So like once we have found out the best combination, what are we gonna do with it? It will just help me understand why we are doing this.
So like once you have chosen that what could be the best hyperparameters for our like model, like in the top where we have put only tune. So it will decide that what hyperparameters, how much trees you need, what tree depth could be best for you, what could be the minimum number of rate. So rather than doing yourself manually, if you have pretty good knowledge, but here we are taking different 100 combinations and then let that decide that what could be the best combination for this data to get our maximum prediction from our model.
Yeah, I got it. Thank you so much.
So it is like, which one you? So I think last time we used the simulated annealing, right, in random forest. So for that, it is like a more slower in the tuning, and it is takes more time for like it is more computational heavy compared to this. Okay, Comfort, go ahead.
Yeah, I just wanted to clarify on the size 100. So when we're talking about the combination, is it like combination of all of these hyperparameters altogether?
Yes, for all this.
Okay.
So here we are doing the 4, but if you are tuning 8 hyperparameters, then it will be the combination of 8, and it will be the 100 combination of 8 each one.
Okay. Thank you.
Okay. So like I will run and it will show the number of trees, minimum learn rate trees. Maybe it will be confusing for you. So if you have seen, so here, rather than showing all, we are showing here number of, so here we are showing on y-axis it's minimum nodes, and on x-axis you have the different tree depth. So it is like a different combination of just 2. So here the bubble color tells you that what is the learn rate, and bubble size is that how many trees are selected. So the bigger the bubble size is, there are more number of trees selected.
All right, so I just wanted to add to that. So can you go back to the code of where you create a XGB grid? Yeah. So right here, we're basically saying, okay, we have 4 hyperparameters we're fine tuning. We want a total of 100 combinations of all those 4. The reason why we're using grid Latin hypercube is imagine, so on our previous exercises, I think we only had 2 hyperparameters that we were fine tuning. Now we have 4, but there's actually, as Arminder showed you earlier, there's a potential for even more than these 4 in XGBoost. So we're just tuning 4 here for an example, but we could find all 6 or 8 that are available. The thing is, the more hyperparameters you have available in an algorithm, you start exponentially increasing the potential combinations in a fixed grid, right? So imagine that you're going to test 3 levels of tree depth, and then 4 levels of min and 5 levels of learn rate, and 10 levels of trees. You start multiplying that, you get a lot of potential combinations, and then it starts becoming more computationally intensive. Here we're using Latin hypercube, which is just trying to optimize the distribution of all those 4 hyperparameters and their values and their combinations into 100 levels. So that's why if you check, I mean, if you go a little bit and show the print here, so there is a total of 100 rows in this data frame because we ask for 100 combinations, but those combinations of all 4 hyperparameter values were optimized to fill in this grid. But the thing is that now, so before we saw a grid with 2 hyperparameters, which was a 2-dimensional grid, X and Y. Now we have 4 variables or 4 hyperparameters that are part of this 4-dimensional grid. So then on the code below this, I mean, maybe let's walk through the code actually to show them what we're doing. So we're just using ggplot to show you 4 different dimensions in a 2-dimensional screen. So we have on the x-axis the tree depth, on the y-axis the minimum n, and then on the points we're coloring them according to learning rate and the size of the point is according to trees. So we added 4 variables in this plot just so we could visually assess where are these combinations in this 4-dimensional space and help us understand how the Latin hypercube worked in creating these combinations. So this is just for us to try to visualize a 4-dimensional space in a 2-dimensional screen, this plot, just to understand where are those combinations happening in this grid. And I guess any questions about that?
Yes, I have a
Good
question.
from online.
I'm gonna mute. Oh, Comfort, raise your hands.
He raised.
Comfort, do you have a question for me or for Raminder?
Yes, I have a question for you. So my question is, since we are confining the combination to 100, does it automatically like select the best 100, or it's just a random selection of combinations? And my second question is, if we increase the number of hyperparameters that we are feeding into this xgboost stuff, does it like improve the model subsequently?
So if we were to ask for more, so size being greater than 100, I mean, we would just get more 4-way combinations of all those 4 hyperparameters. I mean, I don't think there's anything special about the number 100. You could do, you could try more. You could try less as well if you wanted. But of course, the more combinations you try, the better chance you have of finding the best combination for your final model, right? So if you try 10, maybe there would be way too few combinations of all these 4 hyperparameters to find actually the best model. Whereas if you try more, then you have a better chance of finding that combination. Always the trade-off between what is the size of what you want to do compared to computational power that is required to run all that. Okay, so that was your first question. And then your second question, you were asking about if we added more hyperparameters here on this step, if that would be translated to the model training as well.
I was asking that if we included more hyperparameters, is it going to influence the model in a good way?
It will.
It will.
Yeah. So Amrinder, so we decided to only fine tune 4 of them. And whenever we get to the end of this exercise, you're going to see how our test set, our square is going to be. And then Amrinder is going to tell you what he tried on his side that we're not showing here just for simplicity purposes, but he's going to tell his experience with fine tuning this data with more hyperparameter values as well. So when we get there, make sure Amrinder tells you about that.
Okay, thank you.
Yeah,
Let's go.
I tried training with 8, but I got different tasks here, and I will show once we get to that point. Okay, so coming to the next chunk, that is model tuning, and here you are seeing the parallel processing. So here we will do the parallel processing code, like it will use one less. So how many different computers have different number of cores? So but the code which I'm providing, it use the one less core and it will use rest of the core. So this will not do anything with the code, just to faster the computational power, and it will run our code fast. So just do the register. Register do parallel, and then cores is equal to parallel. So detect core, so it will detect number of cores, and usually it is recommended to use 1 or 2. I'm saying less because if you use all the cores, you are not running only R, there are some other software which is running background. It will sometimes it can crash your computer. So it is recommended to use one less core rather than all the cores.
Just run the parallel cores. Just the parallel cores. Just so we can see
Oh.
how many cores you have.
For this one.
We could just highlight parallel with that course.
Nope.
And we could just highlight parallel with that course. With the parentheses in it. Yeah, just run that.
So for me, it is 14.
Yeah, so that's gonna be different for every.
Yes, for every computer, it will be different. What? So it is, we have in the starting, I think I have shown in the library, do parallel. Hmm. It should.
I mean, the fact just called parallel.
Parallel and
Maybe that's what.
so package is known as parallel. Okay. So do install parallel. Oh. So for online, the package name is parallel.
Amrinda,
Yes, comfort.
is the course, is it meant, yours gave 14, is it meant to be the same for everybody?
What? Sorry?
The course at the registered do parallel, you got it as 14?
Yes, it's
Right.
different for everyone.
Oh, okay. Thank you.
It's max. So for online, do this parallel package is working? Or anyone is having an issue?
Mine says the parallel package is a base package and should not be updated, just like yours.
Okay, so when you are running this code, it is working for you.
No, the code is not working too. For the code, it says register to parallel could not be found.
Like
I think
earlier, I do the do parallel, but let me.
And the package is do parallel.
Yes. No. Oh. Oh, it is do parallel, not parallel. Right. So it is work for you? Like I think someone is.
Yeah, the do parallel worked, but not the
Yeah.
parallel.
If let's do parallel, sorry. No, packages do. Or you need both? I think we need both, do parallel and parallel. Yeah. Okay, so if for everyone it works, have you checked the number of course you guys have? It will be different for everyone, like I have 14. So it should be different for everyone. So if you just run this code, whether it is running for everyone online and here. Okay, so now we are using a lot of course for just for R. So it is a good practice. So like once this code is run, so usually it is recommended that after running, stop the parallel processing. So if you use the stop implicit cluster, it will bring your course rather than parallel, everything will be normal. Okay, anyone has question? So, okay, so next thing which we will so we got 100 different combinations. Now, how we have to choose that what could be like a best combination for us. So we will use the function known as tune raise ANOVA. So let me explain a little bit about this. So it will take all the 100 like hyperparameters, 100 combinations from that, and then it will run like ANOVA on it, and it will remove the like it will be on the basis of the speed, like which are the lower values of ANOVA, it will automatically remove that type of the hyperparameters. So which are the best, it will only choose the best one. So like as we sing using the like other traditional search, it could be like slow. It could be wasteful if some parameter settings are clearly poor. So we use this function that is tune race ANOVA to automatically find which are the best hyperparameters to run for our model. Anyone have question for this? Dr. Buster, you want to add anything to it?
All right, so just adding here, I was looking for, I saw once a animation of this at work that may help, but I mean, I couldn't find right off the bat here. I'll share that with you later. But basically, imagine that, as Aminder was saying, we have here 100 combinations of these hyperparameters, of all 4 hyperparameters, and each one of those 100 combinations are going to be run 10 times, one for each one of the folds. So let's say the first combination that we have there is going to be run once on each one of the folds, and then we get for each fold an R-square and our MSE. So we have that variability around R-square and RMSE across the folds, right? For each one of these combinations. So what the tune race ANOVA is doing is running an analysis of variance on a given fit metric, let's say R-square, across all folds for the first hyperparameters that it finds there. And then it just keeps developing which models is keeping based on each one that are performing better. So it's doing an ANOVA at each step, and the combination of hyperparameters that are creating models that are not doing well are dropped from the race. So in the end, the race only continues with the models that are creating the best fit metrics. And that's why it's a race. It's because some of them are being dropped out if they're considered to not be good models, depending on the analysis of variance of the fit metrics across all folds.
And here will be that pruning. Like in the starting, we mentioned about the pruning. So by pruning, it means that whatever the hyperparameters combination which are not doing good, they were dropped out.
Right. Okay, well, I'm going to mute myself. You can.
Okay, so if you run this code, it will take some time. Hopefully, it will not take a lot of time. So you can check is any comma usually or parentheses. No, like I have added the tune race ANOVA function. Have you added that? Okay, so at least for my trend, just this one code. No, just, yeah, all of them. It gives you error. What type of error it's giving you? What? So do you have that XGB specs run? Maybe weather recipe. So you have ran all the codes from the above. It should be, if some objective missing, it's coming from there. It ran. You're getting all 200. Okay, that's good. So like for all 100 different combinations, we are getting both R-square and RMSE. And we are just showing, but it will remove which are not doing good. Is for online, it work for everyone?
Hello, I'm Linda. Can you go back to the previous chunk? Yes, there.
So here we just added this parallel code and tune raise ANOVA function. It works for everyone? Only it works for you? Or it's still running?
Mine is still running.
Not working.
Not working? What error are you getting?
The error is saying that there's an error in workflows. Add the model, workflows, double dash workflow.
So can you run the full code from the top? Maybe you are missing weather SP or anything is missing.
Everything is the same as yours, but
So
it's
like
still
have you ran all these? So just run all the chunks from the above. Just
okay.
click on this triangle button, so it will run all. So okay. It ran for you both, right? You're using, everyone is, maybe they're using, you're using personal computers. Yeah, these computers maybe have more code. I thought with parallel it will do fast. Wally, did you figure out things or still not?
It's still not working, but I think I'll catch up later. I'm
Yeah,
still
like I can help you after class if
yes.
aren't.
Were you planning to talk about the results?
So like we have different 100 combinations of all 4 parameters. So we got like both R square and RMSE for all of that. And now we can choose like what are like, as Dr. Bester mentioned, that we can choose best based on 1% loss, based on if you want to choose based on R square, out of all the metrics, that 200 combination you can choose that which could be the best for you based on RMSE R square, percent, one lost, one standard deviation. So if you, I can talk about next one, it will, or you should wait. Okay, so like in lecture, Dr. Bastos have showed different ways to choose. Like in first class, he showed based on best R square, best RMSE. So lowest RMSE we can choose. So based on the lowest RMSE, the total number of trees, best trees we are getting is 1977. Minimum N is 3, tree depth should be 8, and learn rate is 0.045. So this is based on if you want like a lowest RMSE. And if you want lower RMSE within 1% of loss, you will get different number. So the trees is still same. Everything is the same. So for a best lowest RMSE and 1% loss, it's the same for both. But as you go with 1% of standard error, so it is different for that. So it depends on you, like what type of model you want. So if you want like with the 1% of standard error, then you have to choose different number of trees, different number of minimum and tree depth. this I'm showing you because usually we have seen that we choose based on the best R square, but depending on your objective, that what type of model you want, you can choose differently too. So same based on the best R square with 1% of R loss. So it will be all different. But I just want to show you, like, if I like cluster all 6 together, you have seen that for all 6, there are number different trees, different minimum n. Tree depth is different for different parameters, and learn rate is different for some of them. So does it run, or still it's running for everyone? Run? Okay, so you can run next couple of these chunks will not take much time.
So I just want to add something here too. So in previous exercises, we only checked one of the select type of functions, right? So we started with select best, we went with select one standard error, and then 1% loss, which we saw last time. So here Aminder did a really nice exercise to show you that depending on first which metric you select based on. So if you select based on RMSE or R square, and also the type of selection you make. Either you select the best model numerically and that's it, or you select within a certain range of models being considered, you will most likely get a different answer, right? So then most likely the model here that has the best fit metric is the one that we use the function select best, because that's what's doing, is just getting the best, right? And why do we sometimes may be interested in using the select best within a given range of models? So within 1% error or maybe 1% loss, is perhaps you have like top 5 models that are very similar in R square, but maybe number 1 is very complex and number 10 is the least complex. If you're looking for that trade-off, this is what these functions help you to identify. If you're just looking for the best overall, regardless of how complex the model is, just do the select best. If you want to look into model candidates that may be simpler than the best, but still with a good performance compared to the best, then you would use one of the other select options. And Arminder is just showing you here that if you change the metric, so either if you select based on RMSE or R square, and if you change the function to select the best model, you will most likely get different hyperparameters for each one of those. So just for you to be aware, there's no wrong or right answer, depends on your application, but just for you to be aware that there is different models that can be selected depending on the metric and on the selection type.
Okay, so here now we got what number of best number of trees we are getting, what number of tree depth. So here for this model, I'm using R square as a best. If you want to later on play with best RMSE 1% loss, you can just change best R square here, and it will train model accordingly. So if you run this model, it will run very, very fast. So next come to that validation, that how it's doing like our prediction versus final fit. So if you remember from the previous R square from random forest, CIT, elastic net, usually our model is usually don't do pretty good. Like we got only accuracy for random forest, I think it's 0.07, that's only 7%. And for like the metrics, I use the best R square. So using this, I have gone up to 0.2, that's like 20%, that's pretty good R square. So just to give you like background, so I have used Comfort have asked that if you use more hyperparameters. So here I'm showing you only 4 hyperparameters. That is, we are tuning only 4. But I have, like when I was developing this code, I have used 8 hyperparameters. And the best R square, I have gone up to 0.49. So I have only used the 100 combinations. So if you try with more than 200 combinations, maybe you will get different, and you can get more better prediction. So it all depends that how much time, how much hyperparameters you have, what's your computational power, but you can play with that and see. So I have applied different R square, best RMSE, 1% lost. So with all these, uh, uh, you get different amount of accuracy. So like when I used 1% lost and R square MC, you are getting same. But when you're using best RMSE with 1% of loss, you are getting 0.01855. So it depends that what type of metrics you are choosing, and it will impact your final model prediction too. So it depends again on your objective, and I suggest you, if you want to play with all, just change the parametrics and you will see that how it can impact your model prediction. Dr. Bhai, you want to add anything? Okay, so this is about our testing, and how about our training? So using these 4 parameters, like for training data set, I got pretty good accuracy. So the accuracy which we got for that is 0.99. That is, we are getting 99, almost 100% accurate with the training data set. But as Dr. Bester mentioned, that doesn't matter because your model already have seen your training data set. This is just for you, that out of curiosity, that you want to see that how good is your model is trained on your trained data set. But at the end, we only know when we are doing the running our model on our testing data set. Is anyone having any question online or here? Okay, so next, this is the same predicted versus our observed plot. So here we are getting it's better than random forest, and as though we have told you that this is XGBoost usually is the best machine learning algorithm or the model compared to the other machine learning models. So using our data also, we have seen that we are getting the best prediction compared to the random forest, CIT, and ElasticNet, whatever models which we have run. You can try more parameters and you can try other machine learning algorithms too, but usually it's seen that XGBoost usually outperformed all others if you tune all the hyperparameters properly, and it gives you better results. So last chunk is showing about the variable importance. So as you have seen that mean standard SRD, don't know what it means, but August, we have seen that we usually found all most important variable in all of this. But when I tune all hyperparameters, I got the mean rainfall of August as a best hyperparameters. So it also depends which hyperparameter you're tuning. So it is recommended to tune all as much as hyperparameters you can tune. Okay, coming to the summary. So we learn about XGBoost model. We ran 10 cross-validation. We ran about parallel processing from the do parallel package. And the new thing which we have learned about Latin hypercube and how we choose our best combination using the tune race ANOVA function. So if anyone have question, you can ask me, but if later on also you can shoot me an email if you have any error and want to run the XGBoost on your data set too. So I have provided a lot of resources. If you want to learn more about the machine learning, please have a look into all this. It is really useful resources for all this. And please don't get mad on me. We have the other quiz on ELC. That's not from me, that's from Dr. Bestos.
All right, yeah, so when Aminder was preparing this class, I asked him to create his quiz, which is the one you already took. But I also have one for you. I do want you to work in doubles if you are in a classroom with other people. So work with somebody else if you can to help you go through this. Let me make it visible for you all so you can see what I'm talking about. So quiz number 10 should be visible to you. So basically, I have 4 questions for you. The first one is working with your partner. You're going to have to open the different RStudio projects you did for all the models we ran. You don't have to, well, hopefully your output's still there, so you don't have to rerun it. If you do have to rerun it, then let me know. You're not going to be able to do it in this time that you have. But what I want you to do is to tell me what was the test set root mean squared error of each one of the models we trained. So you're starting with ElasticNet, CIT, Random Forest, and now XGBoost. 4 models. I want you to tell me, working with your partner, you can help each other here. Maybe one of you looks into one model, the other looks into the other. But I want you to tell me what was the RMSE on the test set for each one of those 4 models. Question 2 is going to ask what was the R squared on the test set for each one of the 4 models. And then I ask you, how do they compare in interpretability? And then finally, based on performance on test sets and interpretability, which model would you choose? So again, if you are in the classroom, you can work with somebody else. If you're not in the classroom, then I guess you're going to have to work alone. But work on that. So we have until 11:30. We have 7 minutes. So what I would say is I'm going to already open your attendance issue. After you answer the quiz, make sure you claim your attendance, and then you're good to go. And if you need more time to complete the quiz, that's completely fine. But just make sure you claim your attendance before you go, if you have to go at 11:30.
Dr.
Right,
Ross,
I think that's all I had from my side. Aminder is going to still continue
if you have any questions.
there for questions. We're going to be here for questions, but make sure you work on the quiz as well. And yeah, we'll be here if you have questions.
Dr. Bastos. I think it's full. Oops. Okay. So go ahead and you can ask question.
Can you hear me?
So you can't hear? Yeah, I can hear you.
Yeah, also, I spoke to Dr. Bastos earlier. I'm currently on the field. I don't know if the quiz is still open till later today or it will end soon.
So his quiz is available part time today until what's the deadline? For quiz 10 or quiz 9?
Pardon?
Are you asking about quiz 9 or quiz 10?
I mean, quiz 10. Oh, I mean both.
So quiz 9, I think it's closed or it's still open. He's asking for both. So quiz 9 is already closed, but quiz 10 will be open until noon. So
Okay.
Okay, so quiz 9 will be also open until noon. You haven't submitted it yet.